quantum physics discover negative time, if that's at all possible. In a strange experiment, physicists showed that photons can seem to exit a material before entering it, revealing observational evidence of negative time. How is that even possible? They leave it before entering it. This is mind-blowing. Quantum physicists are familiar with wonky, seemingly nonsensical phenomena. Atoms and molecules sometimes act as particles, sometimes as waves. Particles can be connected to one another by a spooky action, quote unquote, at a distance, even over great distances. And quantum objects can detach themselves from their properties, like the Cheshire Cat from Alice's Adventures in Wonderland detaches itself from its grin. And now researchers led by Daniela Angulo of the University of Toronto have revealed another oddball quantum outcome. Photons, wave particles of light, can spend a negative amount of time zipping through a cloud of chilled atoms. In other words, photons can seem to exit a material even before they've entered it. This is mind-blowing. It took a positive amount of time, but our experiment observed that photons can make atoms seem to spend a negative amount of time in the exciting state is up, wrote Ephraim Steinberg, a physicist at the University of Toronto, in a post on X, formerly Twitter, about this new study, which was uploaded on the preprint server ARXIV September 5th and has not yet been peer-reviewed. The idea for this work emerged in 2017. At the time, Steinberg and a lab colleague, then doctoral student Joshua Sinclair, were interested in the interaction of light and matter, specifically a phenomenon called atomic excitation. When photons pass through a medium and get absorbed, electrons swirling around atoms in that medium jump to higher energy levels. When these excited electrons lapse to their original state, they release that absorbed energy as re-emitted photons, introducing a time delay in the light's observed transit time through the medium. Sinclair's team wanted to measure that time delay, which is sometimes technically called a group delay, and learned whether it depends on the fate of that photon. Was it scattered and absorbed inside the atomic cloud, or was it transmitted with no interaction whatsoever? At the time, we weren't sure what the answer was, and we felt like a basic question about something so fundamental should be easy to answer, Sinclair says. But the more people we talked to, the more we realized that while everything had their own intuition or guess, there was no expert consensus on what the right answer would be. Because the nature of these delays could be so strange and counterintuitive, some researchers had written the phenomenon off as effectively meaningless for describing any physical property associated with light. After 3 years of planning, his team developed an apparatus to test this question in the lab. Their experiments involved shooting photons through a cloud of ultra-cold rubidium atoms and measuring the resulting degree of atomic excitation. Two surprises emerged from the experiment. Sometimes photons would pass through unscathed, yet the rubidium atoms would still become excited, and for just as long as if they had absorbed those photons. Stranger still, when photons were absorbed, they would seem to be re-emitted almost instantly, well before the rubidium atoms returned to their ground state, as if the photons on average were leaving the atoms quicker than expected. The team then collaborated with Howard Wiseman, a theoretical and quantum physicist at Griffith University, Australia, to devise an explanation. The theoretical framework that emerged shows that the time these transmitted photons spend as an atomic excitation matched perfectly with the expected group delay acquired by the light, even for cases where it seemed as though the photons were re-emitted before the atomic excitation had ebbed. To understand the nonsensical findings, you can think of photons as the fuzzy quantum objects they are, in which any given photon absorption and re-emission through an atomic excitation is not guaranteed to occur over a certain fixed amount of time, and rather it takes place across a smeared out probabilistic range of temporal values. As demonstrated in the team's experiments, these values can encompass instances when an individual photon transit time is instantaneous, or bizarrely, when it concludes before the atomic excitation has ceased, which gives a negative value. I can promise you that we are completely surprised by this prediction, Sinclair says, referring to the matchup between the group delay and the time that the transition photon spent as atomic excitations. And as soon as we were confident we had not made a mistake, Steinberg and the rest of the team I had moved on to do a postdoc at Massachusetts Institute of Technology by this point began planning to do a follow-up experiment to test this crazy prediction of negative dwell time and see if the theory would hold up. That follow-up experiment, the one led by Angulo and Steinberg, 2 on X, can be understood by considering the two ways a photon can be transmitted. In one, the photon wears blinders of sorts and ignores the atom entirely, leaving without even a nod. In the other, it interacts with the atom, boosting it to a higher energy level before getting re-emitted. When you see a transmitted photon, you can know which of these occurred. You can't know which occurred. Steinberg says, adding that because photons are quantum particles in the quantum realm, the two outcomes can be superposition. Both things can happen at the same time. The measuring device ends up in the superposition of measuring 0 and measuring some small positive value, but correspondingly, Steinberg notes, that also means that sometimes the measuring device ends up in a state that looks not like 0 plus something positive, but like 0 minus something positive, resulting in what looks like the wrong sign, a negative value for this excitation time. The measurement results in Angulo and her colleagues' experiment suggests that the photons move through the medium faster when they excited the atoms than when the atoms remained in their ground state. The photons are not communicating any information, so the outcome does not contradict the nothing can travel faster than light speed limit set by Einstein's special theory of relativity. A negative time delay may seem paradoxical, but what it means is that if you build a quantum clock to measure how much time atoms are spending in the excited state, the clock hand would, under certain circumstances, move backwards rather than forwards, Sinclair says. In other words, the time in which the photons were absorbed by atoms is negative. Even though the phenomenon is astonishing, it has no impact on our understanding of time itself, but it does illustrate once again that the quantum world still has surprises in store. Angulo and the rest of the team have accomplished something really impressive and produced a beautiful set of measurements. The results raise interesting questions about the history of photons traveling through absorptive media and necessitate a reinterpretation of the physical meaning of the group delay in optics, Sinclair says. This has appeared in Spectrum der Wissenschaft and was reproduced here with permission. First published in Scientific American and by Manon Bischoff on Life Science. Please leave your comments. Thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.